Namaste to all my dear students. I welcome all of you in Antivirus YouTube channel. This lecture will be beneficial for MSc second semester students who are studying statistical physics. In a previous lecture, we have proved Nernst theorem, but in this lecture, I will discuss about the significance of this theorem. But before proceeding further, I will recall the Nernst theorem. This theorem was given by W. Nernst in 1906, and it states that the entropy of a system is zero at absolute zero. That is, when temperature is 0 Kelvin, entropy S becomes also zero. This is very important theorem in statistical physics because it helps to analyze other thermodynamic quantities when temperature is 0 Kelvin. If the specific heat at constant pressure, which is Cp, is known for all temperatures, the following thermodynamic quantities can also be calculated. First quantity is entropy, second is heat function, and third one is thermodynamic potential. So let's discuss one by one. Nernst theorem helps to analyze other thermodynamic quantities when temperature is 0 Kelvin. Before doing it, we recall the power law, according to which this entropy is directly proportional to the temperature, where n is equal to 1, 2, 3, any integer. And this A is a function of pressure or temperature. So this is power law. See, important relation between entropy and temperature. From Nernst theorem, we have proved that the entropy is zero when temperature is 0 Kelvin. Now, like this entropy, specific heats which may be Cv or Cp, and this is variation of volume with temperature at constant pressure and variation of pressure with temperature at constant volume. These all three quantities also become zero when temperature is 0 Kelvin. So they behave like entropy because entropy also becomes zero at 0 Kelvin. These all three quantities also become zero at 0 Kelvin. So let's see specific heat. Specific heats are of two types. Number one, specific heat at constant volume, which is Cv, which is defined as curly Q upon curly T at constant volume, and this curly Q is equal to T curly S. Second one is specific heat at constant pressure. In general, specific heat can be written as C is equal to T into curly S upon curly T. This can be rewritten as curly S divided by curly log, natural log of temperature. Now, at 0 Kelvin, this log term becomes minus infinity. So, this log term becomes minus infinity. So, we are left with C is equal to 0. So at 0 Kelvin, specific heat, whether it is Cv or Cp, they are also 0. Number 2, thermal expansion coefficient, which is represented by alpha. This also becomes 0 at 0 Kelvin. This is defined as the alpha is equal to variation of volume with temperature at constant pressure. This is mathematical definition of thermal expansion coefficient. Now we will prove that how it becomes 0 at 0 Kelvin. We know that this is Maxwell relation. Which is relation between four variable P, T, V, S. There are four Maxwell relations. This is one of the Maxwell relation according to which these variables are related like this. Now, since S is equal to 0 at temperature 0 Kelvin, which is your Nernst theorem. So this alpha becomes equal to minus curly S upon curly P at constant volume. This alpha becomes also 0 because this your entropy becomes 0. Entropy becomes 0. So your this value also becomes 0. And what is this? This is alpha. Hence, at temperature 0 Kelvin, your alpha, which is thermal expansion coefficient, is also 0. Third one is, similarly we can prove that variation of pressure with variation of temperature at constant volume also becomes 0 at 0 Kelvin. This is another Maxwell relation. And we know that at temperature T is equal to 0 Kelvin, S is equal to 0. So this quantity becomes 0. So we can say that this is also 0 when temperature is 0 Kelvin. Next application is the difference of specific heats, which is Cp minus Cv. This tends to 0. This tends to 0 more rapidly than specific heats themselves. The difference tends to 0 more rapidly than specific heats themselves at temperature 0 Kelvin. So let's prove this fact. In other words, mathematically, this Cp minus Cv divided by Cp is 0 at 0 Kelvin. According to power law, we have discussed it previously, that S entropy is directly proportional to T raised to power n, where n is equal to 1, 2, 3, and so on. When temperature is 0 Kelvin, entropy is 0. This is your Nernst theorem. Now let's prove this fact, that difference between specific heat approaches 0 more rapidly than individual specific heats. Now we know the important relation. The difference between specific heat is equal to this. And the term in denominator, this term in denominator, this is called compressibility. And this is not 0 at 0 Kelvin. Because if it is 0 at 0 Kelvin, then this difference will become infinity. So keep it in mind that this compressibility, which is in denominator, is not equal to 0 at 0 Kelvin. Now, since this difference is directly proportional to T S square, here is T, here is also T, and S is here. So this difference is directly proportional to T S square. And from power law, this S is directly proportional to T raised to power n. And this Tn into 2 becomes T raised to power 2n. 1 T is there. So T raised to power 2n plus 1. This is the dependence of difference in specific heat on the temperature. The dependence of entropy is like this, but dependence of difference in specific heat like this, T raised to power 2n plus 1. And this conclusion came from this important relation. This is T. Now Cp minus Cv divided by Cv becomes directly proportional to T raised to power 2n plus 1, and Cp, because Cp is directly proportional to S and which is directly proportional to Tn according to law, according to power law. So on simplification, this fraction becomes proportional to T raised to power n plus 1, which can be written as Tn into T. So your specific heat, whether it is Cp or Cv, they are directly proportional to T raised to power n. But their difference is directly proportional to Tn into T. And if temperature is 0 Kelvin, this difference becomes also 0 more rapidly because there is extra T. Hence, Cp minus Cv vanishes rapidly as compared to Cp and Cv at 0 Kelvin. Second application is, if the specific heat is known for all temperatures, following thermodynamic quantities can be calculated. First thermodynamic quantity is entropy. Since the specific heat at constant pressure is written as, we know it, on rearranging, we can write it like this: curly S upon curly P at constant, curly S upon curly T at constant pressure is equal to Cp divided by T. And S can be calculated on integrating this equation. So we take all the possible values of temperature ranging from 0 Kelvin to required temperature T, which is equal to, this can be written as Cp d log of T. Cp d log of T, one and same thing. And this integral represents the area of the curve between, curve varies from temperature 0 Kelvin to required temperature T. This integral represents the area of the curve. This is the curve. If we plot this log T along x-axis and this specific heat at constant pressure along y-axis, then this is the required curve, and this varies from 0 to required temperature T. So the area under this curve, the entire area under this curve, represents your entropy, provided that we know Cp at all temperatures. Cp, we must know Cp at all temperature varying from 0 Kelvin to required temperature. So this, from this area under the curve, we can calculate entropy of the system. This is important conclusion. Next thermodynamic quantity is heat function, which is represented by W. And this W is equal to W naught plus integral varying from 0 to T Cp dt. I am again emphasizing it that we must know this Cp at all temperatures ranging from 0 to T. We must have value of Cp at all temperatures. Only then we can do. So what is this W naught? W naught is heat function at temperature 0 Kelvin. Next quantity is the thermodynamic potential, which is represented by phi, and this is defined as phi is equal to W minus Ts. We have calculated what is W. W is W naught plus integral ranging from 0 to T Cp into dt, and T, and this is S. We have calculated in first part what is S. This is S. So this S, but How we can calculate this S? This S can be calculated from the area of the curve between temperature T0 to any required temperature T. So from these all quantities we can also calculate thermodynamic potential, provided that we know Cp at all temperature. Thanks for listening and watching.